I also have like a lecture note thing that I also need to actually put on, which I.
It's just there's two different drives, so you might have put it from the one that isn't shared with students.
All right. Well, with all that being said, good morning, everybody. How are you guys doing? Fine. Good. Cool. Awesome. All right. So, as my lovely three assistants have mentioned, the last 2 days.
Boxes.
Not while I'm talking. I'm kidding. So the last 2 days, we've been in what I would consider theory land. So it's going through all the basics, the kind of fundamental questions and like equations and going through the derivations. And I'll admit I am not that person. I am much more of an experimentalist. I like to get my hands dirty and throw stuff in the ocean and see how it works. So as was mentioned, we're going to be looking at how we measure turbulence or turbulent quantities or parameters using specifically acoustic instruments. So that's your ADCPs, your ADVs, your TTVs, your TPADs. I love those sorts of things. Later, Charlotte will go over our microstructure profilers, which are more like strain gauge kind of things. You can correct me if I'm wrong, but yeah, just a slightly different thing with different scales. So moving on, because we're looking at acoustic instruments, it's important to note that the ocean is a pretty noisy place, I'd say. So we use acoustic instruments a lot to understand a whole mess of different properties of the ocean because turns out it's used everywhere. The big thing is that we can learn so much about the ocean just by listening because there's so many different things going on inside of it at any time. I mean, animals use it for navigation, communication. We use it for measuring velocity, getting like sound speed profiles or listening to ship traffic going by. There's a bunch of different ways that we actually use acoustics in the ocean. Now the question is why? So big one is that in the ocean, sound transmits so much more efficiently than light does. Not saying we don't use optical instruments. That is actually another huge field all on its own. But specifically, we use acoustics because one, our speed of sound is about 1,500 meters per second, give or take. It depends on the temperature and intensity of the water that you're in. But sound travels a lot faster than it does in air. So it's really convenient there. And then depending on your frequency, which I'll go into later, you can get completely different ranges. So, you know, it can go on scales of meters to up to kilometers, depending on the frequency you're in. Whereas again, light generally gets attenuated within like tens of meters or, you know, can be longer depending on what light it is. Anyways, so again, we've been existing in theory land the last few days. And so one of the big ones that we look at is the TKE equations. So splitting this up, we have the change like turbulent kinetic energy over time, and then you have a transport, production, and dissipation chart. Now, looking at this, there's a bunch of kind of overlapping values that we want to see. So specifically in like the TKE, you'll see like a U prime bar is what we call the Reynolds stress, which you guys have heard a lot about. Any of these like DU, DZ terms, we call them stresses. Like these are the kind of things that you just want to keep an eye out, and hopefully we'll talk about how you get those. So yeah, first off, what is an ADCP? So they're an acoustic Doppler current profiler. These are a couple of options that we have. So it's a, this is a 4-beam. So these are actual lead zirconate transducers. So that's where the sound is actually emitted. They come in varieties of 3 to 5, basically, so that way we can get the 3 cardinal directions of velocity that we're measuring. And I'm sure probably everybody has at least seen one of these because they're just so widely used. Pretty much every ship in existence has them. They're commonly used on the floor. Yeah, so this is one that I stole from the lab. Don't tell anybody. This thing is worth more than I am. So this is a Nortec 1000. This is a 5-beam ADCP. And so normally you'll most commonly see this kind of 4-beam pattern. This is called the Janus configuration. And And then they added a fifth beam in the center, which I'll kind of explain why in a little bit, but this is kind of more new. But yeah. So, and since we're using ADCPs, one of the big things is kind of where they exist. So again, Charlotte will have a presentation after this looking at microstructure profilers, which are a lot more suited for kind of these fine scale little bits. We saw a paper from I should have put it in yesterday, but from our friend Devin, who did kind of a compilation of both ADCP and the microstructure profilers. And yeah, so this region of, we kind of exist in kind of these wave numbers of about 10 meters to like a little below 10 centimeters, depending on which mode you're in. It varies pretty big. And again, there's a huge thing with frequency and which again, I will go into. But this is kind of the area that you should expect to see. So one important note is that it is actually incredibly difficult to measure turbulence just directly with an ADCP because it's not really in a scale that is convenient, I would say, to measure turbulence directly. So, because we're talking about ADCPs and Dopplers in the name, we're just going to go back to like your intro physics classes of like how the Doppler shift works, because that is what we use to actually measure the velocity in the ocean. So an interesting note is that humans and instruments alike both use the actual pressure waves themselves from sound. So we always talk about hearing different frequencies, but what we're actually hearing is the like wave fronts of pressure coming in, and then there's some funky mechanics in there that like your ear translates those different wave fronts into frequency based off of how far it like goes inside your ear canal. It's really cool. Sorry. But we use the same thing. So we care about the apparent wavelength of sound. So as the source moves relative to us, or just relative to us, the apparent wavelength changes. And if we use our phase velocity relationship, if our apparent wavelength changes, our frequency has to compensate because we're assuming C is a constant. It's not, but in this case we do. So this is the actual Doppler relationship, which we'll use. So this is the initial sound source, which in our case, we're just going to consider to be constant. And then the velocity of the observer, velocity of the source itself, and then the sound speed in the water. So with that in mind, let's look at just a few cases to make sure we are all on the same page. So case one, nothing's moving. So this is just V naught and V source is equal to 0. So if our beautiful ambulance right here just makes a noise, it's just going to radiate out spherically like this. And the distance between these wavefronts is going to be the same. Nothing changes. It's all going to sound exactly how it comes from the source. Now, next case is what if that ambulance is driving towards us? So with that, again, this is kind of you have to think of this in time, but as this is moving, the origin of these spheres is going to move along with the source itself. And so you kind of get this coalescing of wavefronts as it's coming towards you. So what this is doing is our apparent wavelength that we would actually hear when it hits us is getting shorter. And so again, using that relationship, our wavelength is going down, our frequency has to go up to compensate. And so it sounds like a higher pitch. Now on the back end, you can also see that because this is shortening up front, it's actually widening the back. And so wavelength goes up, frequency goes down. Cool. Pretty straightforward. But now, like in the ocean, what happens if we're all moving? So there's a little bit extra that goes into this with the ocean, which I'll talk about in just a moment. But again, so we have a non-zero velocity of our observer, non-zero velocity of our source, and basically the same thing happens just in reverse. So as these wave fronts come to hit us, this one's going to hit first, and then because we move in space, there's going to be an extra distance between the two, and so our apparent wavelength is actually going to go down a little bit relatively. So this is where the relative velocity between the two comes into turn. So the part that I should mention that I don't have a slide on because I don't know why I didn't think about it is in the ocean, it's kind of confusing because we are both the source and the observer at the same time. So what we do with these instruments is each of these faces will like emit a sound at whatever frequency and with whatever pulse we want it to have. And so that will go out into the water column and insonify the ocean. And so what we assume is that there's going to be stuff in the ocean that is moving with the water at the same speed, that all that sound will reflect off of and come back to us. So if you think about that a little bit, you can kind of run into some interesting issues if you don't have enough stuff in the water. So that's actually one of the big things limiting the range and kind of effectiveness of these tools is like if you're in like a super fresh water, there's nothing in it, you actually can't use these really at all because there's just nothing for the sound to reflect off of. But yeah, so yeah, it's kind of weird because again, you insonify the ocean, that excites the particles within it, and then that reflects a wave back to you. The nice thing is that there's also some like sound bending that can happen. I'm getting too much into the actual physics of that, but it's a two-way street and it should be constant regardless. So the other fun thing about ADCPs is the geometry. So this is kind of just a nice diagram view of like what the instrument itself sees. So if you didn't know, ADCPs actually don't make concurrent measurements of the same spot. So these are divergent beams, meaning it gets kind of weird because you're at range, your actual uncertainty of your velocity measurements increases because you're no longer measuring anywhere near the same like water mass or like parcel of water. But the assumption that we use generally is that the statistics here are going to be pretty much the same as it is on the opposite beam. Well, actually, we assume this middle one. But yeah, so the actual angle of incidence that we care about, all of these beams are at the same angle from the center. But yeah, and then if you ever see these shadow diagrams, that's because when we emit a sound, it's not just like, like a point in a direction. They actually had this kind of fun looking beam pattern that we call where it's like, if you have your transducer face, it's actually going to like emit sound like that essentially. And so the width of, oh, I stepped on the thing.
Just wiggled it.
There we go. Wow, that really doesn't. Anyways, that looks like bad. It's not getting those. I do.
Can you unplug and replug your laptop? Oh, I think that's. Remember that we share on the Zoom.
Oh, that's good to know.
Oh, intermission.
Sorry, guys. Hey, there you go. Share.
Remember, guys, he's an experimentalist. He
Exactly.
likes hands dirty.
Exactly. Anyways, it's enough with the peanut gallery. But yeah, so this is like if you ever are like see this and wonder why, it's because our instruments are not awesome, and this is actually a pain in the butt to deal with, especially these little bits, which yeah, outside of scope of this. But moving on. Okay,
Sorry, can I ask a question?
yeah.
So that last slide that you had, oh, okay, so maybe that's like, so the four beams are the, what did you call them, Janus?
Yeah.
Objects, and that's the sound emitting, and then the central beam is the red one that you have highlighted is what?
So that also emits sound. So depending on your configurations, which I will explain here kind of a little bit more. Here, I'll just, it also gives you a velocity estimate. The idea is just that with more beams, you can get a better, like, you can minimize your uncertainty because you're like over constraining a system of equations. So yeah, but So if we take this again, nice kind of front face, and this is my very crude, awesome drawing of just like the top-down view of it. So how these instruments actually work specifically is there are two pairs of like opposite facing transducers that basically create a plane coming across it, which is really fun too, because you can look on these if you guys want to later, and there's actual like an XY coordinate system that they define. But yeah, so the idea is that if you take this plane or one of these planes and you do a side view of it, you'll get something like this, where you have kind of two transducers that are coming across that are the same angle apart, and you get these kind of weird shadows. So the bit that we care about is this kind of a long beam measurement. Yeah, I stepped on the cable again. So now if we take this setup and we actually toss it in the ocean, and there's some sort of just purely horizontal background flow, this would have been better to actually draw it through, but I think the colors make it a little bit easier. So again, we have some just kind of purely horizontal background flow that exists in the ocean. So because we make all of our measurements along beam, you have to actually convert that into what the instrument itself would see. So doing that, this blue arrow, well, the blue arrows are what beam 1 and beam 2 would see of the velocity itself. And if you look at that, you're like, oh, that's not what we want to see. So you have to do some trigonometry. I'm sorry, I know it's a pain in the butt. I deal with this every day and it still haunts me. But yeah, it's a pretty simple expression. So this is what we get, or this is what it's seeing. And then this is kind of the expressions we get. Because there's no W, you can just cancel it out. And it's pretty straightforward, right? For purely horizontal flow. It was just whatever the magnitude of velocity is of beam 1 minus the magnitude of velocity for beam 2 divided by 2 times the angle from vertical. Kaylee.
Is this converting from beam coordinates to earth coordinates?
So this is just beam coordinates to transducer coordinates. And then, so how we actually get from like that to like NEU or ENU, all these instruments have like attitude sensors, so you can tell how it's oriented, and then also you have to, it has a magnetometer and like an accelerometer in it, so you get like actual, like pitch and roll, so that way you can do any adjustments, because it's not always going to be perfectly vertical in the water column. So that can introduce some error, but also it gives you like a relative pitch and roll to like the earth itself. So it's just like a little extra work that you have to go into, but this is generally how we do it. Yeah, I guess that would have been a really good point too. Yeah, but Lex.
For the like 5 beam ADCPs, the middle beam doesn't have an angle with like it's pointing straight up. So how does that?
So that's really useful for the next bit. So if we don't have just like a purely horizontal flow and you actually do put in a vertical component of it, like this kind of solving for this becomes just like a little bit more difficult. So that middle beam is actually just really good at like directly measuring the vertical velocity, which is going to be pretty small. Just because it gets like no horizontal components at all. So it makes that whole bit a little bit easier, but also, I mean, again, this is all just like a system of equations. You have 2 measurements, 2 unknowns. And so it just mostly like that directly measures the vertical velocity and also helps to reduce the uncertainty of these measurements. But yeah. So again, with the horizontal and vertical flow, have the same expression. It's just you don't have, or you have to take into account W. This also works for like the V components as well. I'm just doing one side, but it's the exact same expression as this, just with those 2 beams instead. Okay.
Awesome. So just to clarify.
Yes.
Each beam is measuring the component of the true velocity along its axis.
Yes.
Whatever it's doing.
Yeah.
Yeah.
And so, yeah. With that, like, like deriving all of this, like, this angle that it's going to have relative to like the vertical component, so that you can solve for like that vertical component, and then like yeah, so you get that, and then from there you can figure out like this triangle now, because you have that, and then anyways.
So to get velocity in just one direction, just 2 beams,
Yes.
and then to get the reading,
Well, actually,
to get like meridional lines on the beams.
no, you only need two. Well, yeah, so at the end, sorry, meridional and zonal. So like if you're getting like north, south, east, west, you do have to have 3 beams, just because again, system of equations, 3 unknowns, you have to have 3 sources of information that kind of converge on all of those. So this is, but in this case, like with just the north and south, like you only technically need, like, if it was, yeah. Sorry, wait, what's that? Okay, yeah.
I think you answered my question.
Okay, that's
That's fine. Yep.
I think I'm still trying to get myself to the same.
Yes,
So I think that this ADCP is looking down into the skin.
yes,
It's like vertical here.
yes.
um, And so on the last slide, view was, but I only actually now it's too.
Yeah, sorry. I realize that might be confusing. Like, think of this as like vector U, not like east, south U. I should have explained that better. I'm so sorry. I realized that was going to be an issue that I forgot to mention while I was here.
So is the horizontal because W is 0?
What's up?
Is the horizontal vector?
Yeah, so in this case, like U would be just like the horizontal, but I didn't do a good job of like notation. And so this U is not like purely the horizontal vector at this point. It also has like, it is just the velocity vector, which I should have.
You did label it true velocity.
Yeah.
Okay,
It is true velocity. You could just relabel the red arrows as U plus W for this slide.
that would probably have been the
In,
best.
yeah, in this case is the total vector, but in the slide before, well, it's just horizontal because W was 0.
Yeah.
Uh,
Good questions. Anything else before I move on to the next one? Cool. Okay, so the other bit is, again, so depending on your actual frequency of the sound that you're putting into the water, that will really affect your range and also the like, or the like spatial resolution of your bin. So, an important note with ADCPs is that like you can't just get like a continuous measurement of velocities all along axis. We have to do some amount of averaging over a spatial period, which is basically tied to like here actually I will just so like a common thing that you'll see is what we call coded pulse. So like it's just basically some like repeating value that like we tune that should not exist in the ocean in any form. So yeah. So how we actually like do these measurements is we spit this out. There'll be like a series of like a few of these in a row. Like I don't know, like the project I use, we have 7. It's cool. Anyways, so we spit this out, and our bin sizes are dependent on the length of this and like how far like basically how far this code picks up in the water itself, because once that reflects off the stuff in the water, like we have to come back and actually compare that to a signal itself. We call through the like covariance method. Basically, we take this we compare it to like what we know it should be, and then that's how we actually get the Doppler shift itself, because as this comes back, like the frequency of this will be a little bit different. And so when you take the FFT of that, you'll see like peaks at a certain thing, and like that will just shift around a little bit. But in order for us to actually make those estimates and like kind of average over it, we have to wait until this entire pulse can go through like a volume of water and come back. And so depending on how long that is, that affects your bin size of itself. And so you can imagine at low frequency with like really big wave numbers, that's why we get really, really big bins of like tens of meters at times. But at really high frequencies, so like the 2 megahertz range, this is like centimeter scale or like smaller. Yeah. And so with that too, again, I mentioned low frequencies, they can kind of just propagate through the ocean, not indefinitely, I shouldn't say that, but really, really far before they actually attenuate in the water. Whereas high frequencies get absorbed like immediately. And so that's why our range is just so much shorter for the high frequencies. But this is just a handy table to kind of get like a general idea of what resolution and range you should kind of expect to see depending on which like instrument you're using. Just because, yeah, this leads into the next bit of, because there's a big trade-off between resolution and range, it is not uncommon for people to use multiple ADCPs of different frequencies. So as a fun little bit, I thought I'd add in some tools that we see on our ships. So
Sorry, I was just thinking about the last slide that you have. So for the like the high frequency ranges,
Yes.
It almost feels like because you're so close, like in the 5-meter range, that the ABCP would affect the experiment in itself too.
It can, yes.
So,
Get
like-
turbulence off like the
Yeah.
structure itself. That's why, yeah, you have to just be really careful. I mean, it's the same thing with like that's like those kind of ranges are usually seen on like landers on the bottom. So like I've seen people use them for like sediment transport or like that kind of stuff. And you just have to be really careful, but yeah, it's like using the demo again here. Like, you know, generally flow going by, I mean, you're gonna get like a little bit of a boundary layer across the face. But you just want to have the space like far enough that like this flow is generally just like not interrupted. But if you're trying to measure something from like the backside, that's where you start getting into considerations. And like that's why you'll see landers are like super, super wide. So they'll have like, you know, take up a huge thing, and then they'll have just like a little ADCP in the middle, mostly to try to decouple any of the like turbulence that comes from the like physical features itself off of it. Also, for the ship mounted stuff, we'll see it where that is very precariously put in here. Ship dumps. We also do a little bit of processing ourselves where basically these first like bins or two, we just ignore. It's called blanking. One, because when you emitted sound, like everything around it would also kind of insonify and kind of echo around it, especially on a ship. And so you can get a lot of contamination in those first few bins. And so we just ignore them usually. But that also, at least for like the ship component stuff, also like helps ignore turbulence like coming from the hull itself. So there are ways around it, and you just kind of have to be careful. So
are the different frequencies scattering off like differently sized scatters?
yes.
So do you have to like the scatters in regions of the ocean change quite quickly?
Yes.
Do you have to like retune as you're going what kind of beam stuff you're using, or
Not too much. You actually don't really get a lot of play. I haven't used UH-DOS too much, so any of my friends around here. But that's so UH-DOS is like this software that everybody uses for all these ADCP things. So you can get like you have some amount of control to like adjust, you know, what your expected range should be and like what your resolution and bin sizes, but I don't think you can tune the like frequencies too much. So because of like how these crystals work, which I can show plots later, but so generally that's why we have like multiple. So like you kind of get, I don't know, it's kind of luck of the draw too, because like we had it on a couple of cruises where like we expected there to be stuff and there's just not enough stuff to actually get a signal. And so like it just kind of sucks. Like we have one instrument that our lab uses that's on the Ravel that can vary in range from like 1,500 meters to like 600 meters, depending on like just where in the ocean it is. So it's kind of just luck of the draw.
I guess, so is your question like, it seems like you're explaining it kind of like as a binary, like there either is stuff in the ocean and you get a signal, or there's no stuff and you don't. But is there a gray area where like, I mean, if the scatter is moving, obviously that affects the Doppler shift. So are we assuming that the scatters aren't moving?
That is a good point. So you actually can see.
Is your question?
That's another interesting question.
Okay.
So yeah. So part of it is like you're saying, so particle size in the ocean that matters. So it's like really big particles will cause just like a window to appear. So like I don't know if anybody sat in on like I think Jonathan Nash's talk or somebody else recently again that was doing sediment transport, where it's like if you get too many particles, then like it just blocks out your signal completely. Like it creates a wall, which is another thing that happens is like, if you have like really strong scatters at like one point, then like your beam cannot physically penetrate that. And so that could artificially cut off your range and you're just kind of screwed at that point. Also, bubbles are a big one, which I don't really remember what the relationship is. I think it's high frequency hates bubbles.
Also depends on the size of the bubbles. There's like a lot of factors here, like Austin is talking about. But you have the particle size, and then how many of them there are, and then what your instrument is constructed for, and like what platform you're putting that instrument on as well. So like Austin was saying, for ships typically, there is typically a 75 kilohertz, a 150 kilohertz to get like slightly deeper. On the sprout that we're going on next week, there is 150. Wow, look at that. What you're gonna get to play around with. We also have a separate ASP that we're bringing that is of 300 kilohertz that you can also get to play with if you want. But yeah, and like at some point, it's just experience almost that, or yeah, you will learn which instrument to choose for which kind of situation and what kind of needs you have in terms of range, where you are, what platform you are, what the power supply you have. That's another factor. Because on a remote platform, like on a self-contained platform, you need to supply battery to it, and ACPs are quite battery hungry. So there's like many different factors to take into account here.
You say again, why only get so many bins?
Yes. Yeah. So the big one is again wavelength. So high frequency, your wavelength is relatively small, and so if we have the same code that's like we'll say 10 wavelengths, then we need to have like a little over that technically to get a sample inside that. And so that is kind of what determines your bin size. So like high frequency, small wavelength, your actual bin size itself can be a lot smaller because like the actual 10 wavelengths of sound that you need to get an average is just smaller. Whereas like low frequency, it's the opposite. Does that make sense?
Yes, totally.
No, that's fair. I'm a little scrambled right now too, if you can't tell. But anyways, so
You're doing great.
thank you. Please don't call. So this is where we're at. The Sproul has one. You guys are bringing one. The Ravel has just 3 different ones that it uses, but that is also just the ADCPs. There's other fancier forms called phased arrays that also exist, and then ONR has parents. But yeah, Also a handy thing too with like picking the right instrument is like the size of these goes roughly with the wavelength itself. So this is a relatively small guy because it's, I want to say, oh, I should have had this memorized. I want to say it's like, I actually don't know what the frequency is.
Trying to remember the frequency.
Yeah, off the signature 1000 kite, you might know.
Isn't it? I think it's
Is it 1,000?
Signature 1,000.
Yeah.
What's in the name though?
Yeah, I feel like they.
It's called.
I don't know.
1,000.
Because what else? Would go with that?
Well,
Workhorse 300.
Well, okay, yes, like most of them have it. That is another thing, is like most of them have it in the name. I want to say the signature 1000 is different though, but that might just be. Anyways,
Right now.
but yeah, so like this, the size of them like scale with it. So like your 75 kilohertz being like a really low frequency is huge, and that's why it's on the ship. Yeah, okay, so take all this ship measurements of along track velocity and shear. So shear, we're just doing the du dz kind of thing, and so we just literally take the difference of like our vertical bins and then normalize it by the actual size of these bins themselves. So this is the Workhorse 300 kilohertz ADCP off of the Thompson from some field work that we did last year in India. It was great. And so you get these nice like fun bands of like velocity, and then the real star of the show in most of the cases, what you'll actually be looking at is the shear. And so you can see these kind of like nice space bins of like roughly 10 meters. Those are just internal waves that are propagating, which I thought was really fun when I actually processed this a little bit. But yeah, and then also go from there. If we do the Reynolds decomposition, take out the mean, just track the anomalies, you get like a completely different picture. And like this is just showing like the along track variation of kind of those jets that we're seeing.
Yeah, why the fingers are black, is that the bottom, and why they have colors over the black area?
Yes, so that is our effective range. So in this case, with the 300 kilohertz, we're only getting 80 meters. This was deeper at different parts of the cruise, just for this snapshot specifically. I think this one is tuned to like 200 meters range regularly, but there's just like not a lot for like, there's not a lot of scatterers in this part of the ocean that we were at. And so our regularly 200-meter range got cut off to like 90 meters.
So the ADCP is at 200, but you can see over 100? Sorry, I lost that part. Where is the device?
Oh, this is on the bottom of the ship. So
Okay.
it's like on the
Yeah.
bottom pointed down. And so
Okay.
normally we should see 200 meters depth,
Sure.
but in this case, we're only seeing up to 90.
And why you can see the surface? Because the noise of the ship or something like that?
Yeah, and so for the ships especially, it's like when you emit your sound, it's going to bounce off the hull, because a lot of times they're like in recessed cavities in the hull itself. And so because of those, because of like, remember the beam pattern I drew, like little side bits, those just go off sideways and then come back into the beam. And so what you're not actually hearing the stuff in front, you're just hearing the returns from the side. And so that's why we have to cut off a little bit extra, because it contaminates.
I don't know, it depends. I understand that the configuration of the ADCP to know where you need to cut.
A lot of the time you'll see, so when we get these measurements, we'll get like an intensity of the return itself and like coherence and a velocity measurement as well. So we usually just cut off, like if you plot the intensity, which I can pull up in a little bit of some other work that we've done, you'll basically see like some like normal value or like just kind of a regular intensity. And then like up here, it will be like orders of magnitude higher. And so that's how you know that you're getting some weird
It's not
side
right.
lobe from machine. Yeah.
Okay, thank you.
Okay.
So the data that you get, is it just like the velocities directly beneath it?
Yeah.
So you don't get any information about like stuff?
Not really looking. So depends on how like deep you want to get into it, because it's technically we're getting a velocity estimate on each of these beams.
Can you repeat everything?
Yes and no. So generally, we assume that like the velocity that we're measuring is actually along this kind of center beam. That's like how you'll usually look at it. But if you get a little deeper, you can actually physically make these velocity estimates off of all of them. And so you can get kind of an understanding of like a larger area rather than just this like kind of assumed center beam down the middle. But if you do that, then like it's again like you kind of need these like opposing beams to like get actual like cross velocities of like the entire thing. But you can get stuff out of it. So generally the assumption is that we're measuring along this kind of center beam and just kind of averaging horizontally across each of them to get velocity. And that's why, you know, like as this goes out, you're like averaging over a very large area where it's no longer like actually related or like they're at that point they're pretty much independent, but like we make the assumption that they're not. Yeah, but we have other fancy things that actually like do measure physically in like a fan shape, which is a different thing. But Tom.
So I have one last question, because this is what I was thinking about earlier with the, because yeah, so you're measuring speeds along track and
Yes.
across track, depending on where the ship's going. And then do you also convert these to like a zonal and meridional? And then how's that done? I mean, do you like have a GPS on the ship?
Yeah, so yeah, we have the ship GPS itself, and then also like in the array itself, we have like a tilt sensor. So like you get those kind of tilt corrections, and based off the ship itself, it's usually like mounted in a very specific way. So that way it's like in reference to like the keel of the ship. And then from there you just get a heading, and that gives you, then you can just rotate it into, so like that's actually what I did with this data set. It's like it pops out as like we do it in like in a long track velocity, so that's like going with the ship. And so I did actually convert this at one point into like ENU just by taking the like the yaw of the ship itself and then correcting that into
Okay, gotcha.
Yeah. Anyways, sorry, I gotta speed up here.
You
So
have 15 minutes that we stole from you in the beginning.
I don't know if anybody wants to hear me chat that long. Anyways, the other fancy tool, which I'll spend less time talking about, is called ADV, or an acoustic Doppler velocimeter. They basically operate on like the same principle as ADCPs, but the big difference is that rather than having divergent beams, you have your beams converge onto a single volume. And so we actually consider these to be point source measurements of velocity. But yeah, same Doppler shift, same bin size, the frequency, all that kind of stuff, except it's all just focused in on one itty bitty point. And because of that, these are particularly suited for measuring any of those like fluctuating terms. So like you can actually just directly measure like your Reynolds stresses with these guys, which is very convenient because with ADCPs, because of the scale, depending on like which frequency you're using, it can be very difficult to actually get a good estimate of your Reynolds stresses and like some of the other turbulent parameters. Whereas these guys are like specifically tuned for it because it's just focusing on a single one. But with the trade-off of, again, you are only getting one point of data rather than like an entire wire column's worth. So that's part of the distinction. Yeah, okay. Oh, so again, talked about a lot of the kind of engineering physics that goes into it and why we do what we do. And let's actually go back into turbulence land. So, you know, just reminder, this is what we're looking at. A few of the things. So Reynolds decomposition. So again, we just get kind of a velocity estimate in our UV W coordinates. Generally what we'll do is use a time average because either it's like a stationary point and so spatial isn't like super great, or like we're dragging it. So like if you're not going at consistent speed, it's really hard to get like an actual spatial average of things. So we use time average, and generally speaking, the rule of thumb, it varies from like 2 minutes to like 15 minutes to do your like kind of moving averaging window of your velocities. And that is entirely dependent on basically the frequency of like the or like the frequency of the wave number of the actual things that you're trying to study. So for like, high speed kind of turbulent things, you really want a small averaging window and really high frequency. So that way you're measuring the same point. Cause yeah, I don't know how you guys feel about aliasing, but it's a whole thing. So that's kind of a trial. But like if you're doing big scale stuff with like ADCPs generally, it's like 10, 15 minute averages. And then yeah, perturbations are just everything left over after that. So few case points. Reynolds stresses. So you have your time average, U primes, W primes, or V prime, W prime. If you just look at specifically the beam velocities, it's pretty straightforward. So you just do your Reynolds decomposition of the actual like beam velocities that they're measuring, take the primes, square them, average it in time. Same thing. Yeah. I don't know. This was
Beam 1 and beam 2,
Yes.
would that be like the opposite beams? Okay, and then 3 and 4 are the other opposite beams?
Yes.
And then the middle one is not needed in this case?
No. You can. There's like it just adds in like a huge thing. I can send you guys a paper on that if you want, but it takes this like couple of like nice succinct thing and like makes it this long kind of thing, adding in the fifth beam. So again, that's just like to reduce your uncertainty. Actually, interestingly enough, adding that fifth beam does not appear to actually help with your estimates of Reynolds stresses too much from what I've seen, or the papers that I read. So interesting note. But yeah, so there's that whole bit. Turbulent dissipation. So this is one that kind of we talked about like, you can get the shear spectrum and like back out EPSI from that. But I wanted to talk a little bit more about structure functions, which I don't know if I'm necessarily super qualified to talk about this. So I will do my best to explain. So what we do is start with a second order structure function that is like dependent on both depth and the actual range from your beam itself. You create like a time average squared difference of like the turbulent like bits along your beam. So like for each individual beam of your ADCP, you can create an estimate of, or like you can create your own structure function for it. And basically this distance that we're concerned with is like our bin size. This scales with the size of let's see if I can let me skip forward a side. So that distance R in our structure function is dependent on the actual size of the features that we're expecting to see. So ideally you want to like tune your bin size to be roughly the same distance R of like what you're trying to see. So again, for like really low frequency ADCP, you're not going to get anything super useful, but for like a pulse coherent ADCP that's higher frequency, that can actually get that kind of lower end, or yeah, that value. I don't know.
Smaller bit size?
What?
No.
Anyways, yeah. But you can get those kind of smaller turbulent features a little bit easier.
Sorry, the first time I heard of structure functions was yesterday. So to be clear, when you say structure function here, are you just saying you're assuming it's quadratic and you're fitting a quadratic to your data?
Essentially, yes. So we have this kind of like, if you take the kind of canonical shear spectrum that we have, that is just like an empirically measured thing that we've kind of toyed with over the years. And so the assumption is that you're expecting to see that. And so you're taking this kind of nice quadratic, like you're saying, and you're just essentially fitting it to it. So there's a couple of papers that actually connect this value. So I should have put this step in, but like you can set this equal to like S prime squared. And so that is then how you get this kind of expression of like, this is supposed to be the Kolmogorov constant, because this is the atmospheric one, which is just, yeah, these are just basically different values. But essentially, yeah, you have like this ideal spectrum shape that you're expecting to see. And so you fit this value to it through a series of like constant terms. Again, I learned about this about a month ago. So I don't know if I'm, again, as qualified to talk about this, but the assumption here too is like, getting at those like small scales, you introduce some like instrument noise. And so like, if you were to actually directly estimate, like your spectrum from it, you get this kind of like overestimation of it because you have some amount of noise that you're not taking into account. And so there's like some stuff that you have to get through to estimate this to actually bring it down to where you're expected to see. Yeah. And then going forward, you solve for some constants, and then from there you have an expression for epsilon. Going back to it. So I will actually have a better explanation of all this in my lecture notes, which I will post in a little bit. But that is kind of my general understanding of the whole process that goes through it. If anybody else has something to contribute, please do. If not, in the interest of time, we'll go for it. Okay, our next turn, turbulent kinetic energy production. So we are missing the like, was it D rho T prime term? We're not concerned about that right now. We're mostly looking at momentum terms. So for that, it's pretty straightforward. It's just our Reynolds stress times our shear plus our other Reynolds stress times our other shear. Pretty straightforward. That's how we estimate it. And then, yeah, I thought I had another one, but that is kind of the extent of my spiel. I hope that wasn't too confusing, and I hope you guys got something out of it. If you have any questions about any of this, these are some of the like most helpful things that I found coming across all this. So this is just like a really well laid out explanation of like ADCPs and like how they work from Nortec itself. Kaiki put me on that, which was awesome. But it goes through the whole process basically, and like there's some more explanation of like the different signals that you send out and different applications. This is particularly good if you're going on a cruise and you have no idea how an ADCP works or how to set it up. Is like the or book I'd recommend. And then this just kind of summarizes all the like turbulent bits and how you get it from different things. And it was just a really good page. So
And also do a quick shout out to like, if you ever have to set up an ACP yourself and like it's just built into the ship and you can do a full ACP or something like that, definitely spend some time playing around with like the UH-DOS and like website and stuff. They have a lot of tutorials and things. Make sure you have a Mac on hand because all their stuff is written for iOS. But yeah, it's a lot of people spend a lot of time making things that work, and it's not quite as easy as just plug and play, but it definitely is something that you do not have to reinvent the wheel. I also looked up the signature 1000. So their AST frequency is 1 megahertz.
Okay.
Which I assume is
it's 1,000.
Is right.
That's 1,000 kilohertz.
1,000. So that makes sense. But they have a 16 hertz kind of like frequency, I guess. So you're getting 16 measurements per second, and they're like frequency measurement, which is maybe why you got confused about the numbers there.
That doesn't make sense. Cool.
Okay. The documentation's a lot, but regardless.
Oh yeah.
People have used an ADCP before it. Or like looked at ADCP data versus like actually like used an ADCP and set it up yourself.
Which one?
Any ADCP. A couple, yes, no, yeah.
I use HTTP data, but already filtered, so I never seen raw data and how to convert all the stuff.
The processing stuff, yeah. So
Exactly.
so just to clarify what people were saying, UH-DOS kind of thing, that is actually from University of Hawaii. There's
the
a
H.
That's
Yeah.
the H. The H in UH-DOS is Hawaii. So they have a group there who have put a shit ton of time into put it like how to process and how to set things up. So they have like super good guidelines. And today, if you go on any of the UNOLs, which is the University National something of ship time kind of thing. So all of the North American institutions that get together like share research boats, UNOLs. And so if you go on a UNOLS boat, like the Ravel or the Thompson or the Sproul that we're going to go on, they have UHDOS, like all of the latest stuff installed, so you basically just like navigate to the right folder. And you get like a file, not file or NC file.
They do all the work
They
processing
do all the
for you,
parts.
but I'm saying like, if you ever have to set it up, you can in fact do it yourself and like, it is
Exactly.
annoying, but like, it is very doable, and I just wanted to mention that because when I first had to do the full ADCP thing, I was like, oh my gosh, I have no idea what I'm doing, and like, usually the ship will do it for you, but don't become complacent, like, sometimes you have to do it yourself.
Exactly, so Andrea has put it on a poll, so most research boats have ADCPs installed in like the bottom hole of the ship. And they just are on all the time, and they look down and they like measure the velocities for you, and then that data is collected all the time and it's shared and so.
The thing is when you go back and forth on a boat, right, because you're changing directions, it makes it like the ADCP doesn't know necessarily that you've changed directions, like it has a compass in it, but you have to like, in the code, you have to basically tell it like, you have now changed directions, because it thinks that the currents have flipped directions because you're now going the other way.
Exactly.
So when you have to, the ships already have all the stuff set up, so you don't have to worry about it. When you do it yourself, that ends up being one of the biggest frustrations. But it is, again, one of those things where like, if you have a full ACP, like, again, you on your own computer can log all the data. There's like, like, if you ever need to do it, just, is software. I just wanted to mention that it exists. But hopefully you don't have to do that anytime soon. It's a bit annoying.
Yeah. And then, yeah, there are other situations where the HCP is on a platform, a different kind of platform that is moving. And then this is what Austin has been talking about. You did not even mention TPAMs.
Well, I was doing ADCP.
ADCPs. Austin is part of like figuring out a way to put ADCPs on a platform that is not just profiling or staying still, but is actually like towed behind the boat. So instead of getting just like
well, it's the fact it's lots of ADCP living next to each other.
yes. And it's so you instead get a swath of velocity. But yeah, go bug him about that because that's some really cool, and he will show you some cool plots and stuff. And it's really, really
It is very fun, I will say.
Yeah.
But it is a mind.
There's a lot of trigonometry and a lot of like, yes, orientation, where are we in space and time, etc. But yeah, almost around next week, we're gonna have ADCP data from the boat. And we also have a lowered ADCP with us that we can put on the cassette, and we can show you how that works, and you can get to practice, talk to it, and sending startup files and stuff if you want.
With that, I think we should take a break,
Yes.
and you guys can absorb all that information and ask